Do not start the determine the state of stress combined loading problems with method of sections and finding forces and moments. I know that's probably what your textbook says, but my way is better. Start with your equations for normal stress and shear stress. This gives you just 4 terms. Your N over A is axial loading, My over I bending, Tc over J torsion, VQ over IT transverse shear. This basically just gives you a checklist. If you find all of these things, N, A, M, Y, I, T, C, J, V, Q, I, T, 12 things, you find those 12 things, the problem's done. You just have a checklist. And to make this even more horrible, I'm going to do it actually 3 times so you can see the differences between different points, A, B, and C on my drawing. And I'm going to tackle them axial loading, then torsion, then bending, then shear, basically from easiest to hardest, because at least that way I can make progress faster and I won't give up as easily. So N first, just look at each of the 3 red arrows, each of our forces. Are any of them causing this rod to stretch axially to get longer? And only one of them is the 100 kilonewtons. So N is 100, and it's the same for A, B, and C. The same stretching is the same everywhere on the bar. So we've actually, boom, just check mark that. All right, next. All right, next, cross-sectional area. Pi r squared, we're given the radius, so 0.002 whatever for the cross-sectional area. And now we have N over A, so we are 1/4 of the way done with the problem. Sort of. Not by time, only by category. Moving on to torsion. So now we look at, again, all 3 red arrows. Which of these 3 are causing the bar to torque? Which ones are twisting? We see the 100 is not, right? It's lengthening. Both the 10 and the 20 are causing torsion, so we're going to have to account for both of those. Good news is they are both causing twisting in the same direction. Kind of looking at it from the end, they're both causing clockwise rotation. So we can just add them up. So our T value is just going to be this 10 plus 20, so 30 times the radius, right? Torque is force times distance, just like moment, just about a different axis. And now we've got our T value, 0.9 kilonewton meters. C is going to be the distance for each of our points of interest, A, B, and C. How far away are they from the center? Because torsion is 0 right at the center. Furthest away you get from the center, you feel more torsion. So in our case, all 3 of these are just the radius away. So C is just going to be 0.03 meters for all 3, A, B, and C. And moving on to J, polar moment of inertia. I never remember this equation, so I always have to look it up. And the main thing I have to remember is there's 2 different versions, one for diameter and one for radius. So easy mistake to make is to use the wrong one. Just make sure we have 0.03, so we want to use the version with radius. So 0.000000 blah, 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 12. And that's our value for J. We're going to plug all the numbers in at the end. Right now, again, we're just going through this like a checklist. We had 12 letters that we needed to find, just 12 variables. We're just going through in order, easiest to hardest, just finding one and checking them off. We'll plug in the numbers later. Unfortunately, this is where it's going to start to get really annoying because A, B, and C now are going to start being different once we get to bending and shear. And that's why I wanted to do all 3 examples so that you can see the differences between them side by side. The 100 kilonewtons causes bending only to the side, so we can ignore that one. Same with the 20. It's also causing bending to the side. We can ignore that. Only the 10 is causing bending downwards. So our My over I, the M, is going to be the 10 kilonewtons times 0.4 meters leverage it has from the point of the force to our point of interest. Area moment of inertia, I for a full circle, you'll probably have to look this up in a table, 1/4 pi r to the 4th. Plug in the numbers, 0.00063, and that is meters to the fourth. Again, this is not to be confused with the mass moment of inertia. Think of like the mr squared that you might see in a dynamics class, which would have units of mass, like kilogram meters squared. Area moment of inertia is an area times a distance squared, and so meters to the fourth. Then y, distance from the neutral axis, point A is just the radius away from the neutral axis, which is the center of the rod, so 0.03 for y. So that's bending for point A. For point B, now point B is very similar to A in that it is also looking for bending to be downwards or upwards. But the difference is that the sign is going to be the opposite. The 10 kilonewton force is doing downward bending, which is causing tension at A, but compression at B. But the magnitude of the force is the same. M, Y, and I are the same for A and B, but later on when we go to get the final answer, there will be a sign change difference because of tension versus compression. Point C, though, is going to be different since C is actually looking for forces that are causing sideways bending. For the 10 kilonewtons that's bending downwards, C is on the neutral axis from that force. So C is actually interested in bending from the 100 and from the 20. And both of those are causing bending to the right, which is the direction where C is going to be in compression. But we can get our value M just using the leverage arm. So 20 times 0.2 is how much leverage. That 0.2 is perpendicular to the 20 kilonewton force. And then the 100 kilonewtons has a leverage arm of 0.03, just the radius of the circle, right? It's not 0.4 meters. Remember, when calculating a moment or a torque, your force and your distance have to be perpendicular to each other. 0.4 is parallel to the 100 kilonewtons. The perpendicular distance from the 100 is 0.3. Get 7 kilonewton meters for the moment. And good news again, Y and I are going to be the same. So we don't have to recalculate those. And now we're 3/4 of the way through this gigantic, monumental, annoying problem. The last step is transverse shear, which is the worst one, but let's push through. We're almost there. Shear, VQ over IT. I is the same as before. So we actually already solved for area moment of inertia I. We can just reuse that same value. T is the thickness at your point of interest, so at A, B, and C. Now, if we're only looking at this from one angle, it might look like the thicknesses will be different, but when it comes to shear, shear is maximum on the neutral axis, and it's 0 when you are the maximum distance away from the neutral axis. So point C is going to be relevant for our vertical forces. In that case, C is going to be on the neutral axis for a vertical force. Let's look at a quick example. The 20 kilonewton force is pointing sideways. The neutral axis for shear is perpendicular to the direction of the shear force. So the neutral axis is vertical. This means for the 20 kilonewton force, A and B will be relevant for shear, but there'll be 0 shear at point C. And so all this was a way to circle back and say that the thickness is always going to be the diameter for A, B, and C. The thickness at C is the horizontal diameter, 0.06. The thickness for A and B is the vertical diameter, because again, that applies when we have the horizontal force and a vertical neutral axis. And the 100 kilonewton force is just getting ignored here, right? It's causing axial loading. It's not causing sideways shear. So it's not involved, only the 10 and 20. So let's do first A and B. I'm highlighting in orange the part that if shear happened at A and B, right? If the piece actually sliced in half at the neutral axis, how much area would get sliced off. All of the area further away from the neutral axis than point A, which is a full semicircle. So V is 20 kilonewtons, that's our shear force. Q is A prime Y bar prime. Q is the number one thing that more students will mess up during this course than anything else. The entire Mechanics of Materials course, Q is the overall number one most common mistake. But it's not that much more difficult than everything else. You can get this, right? A prime, Y bar prime. A prime is the area of the section that would get cut off if it failed in shear. So it's the area of the semicircle. So pi r squared over 2. Y bar prime is the centroid of this area. So the centroid of the semicircle. And I don't expect you to have that memorized. You just look that up in a table, 4r over 3 pi, plug that in, multiply it together, and that is your Q. It's 0.0000018 meters cubed. Again, the units are meters cubed for Q because it's an area times a distance. So we've got V, Q. We already had I. We've got T. That is, oh, okay, sorry, we got to do point C. We're almost done. Okay, point C, we've still got now V of 10 kilonewtons. But actually, Q is going to be the same because it's still just this same semicircle. So the area of the semicircle is the same. The distance to the centroid is going to be the same. The thickness is the same. Yeah, so actually, we can go and start plugging in numbers now. So we plug in all the numbers we found throughout the problem, but now is when we actually have to take a look at sign convention. Do these forces help each other? Are they pulling in the same direction, or are they opposing each other? And there should be some minus signs involved. So for point A, normal stress, the 100 is stretching, right? That's positive in tension. And the bending force that's happening, since the bending is downwards, the top at point A is also in tension. So both of these forces, or both of these stresses, get added together, and we get 224 megapascals tension, normal stress for point A. Point B, the same axial loading and tension, but for bending, the downward force causes bending at point B, which is on the bottom of the rod. So there's a negative sign in front of the bending term. This ends up giving us an answer of negative 153 megapascals. So we are in compression at point B. Even though the 100 is causing it to stretch, the bending is a bigger effect. The point B is actually facing compression overall. Similar thing for point C. The 100 is causing axial tension, but point C is in compression due to bending from the 100 and bending from the 20, and these bending terms dominate, so we end up with a negative 295 megapascals, so a compression at point C. And it's kind of an interesting little aside that the 100 kilonewton force is causing both tension and compression. From axial loading, it's causing tension, but from bending, it's causing compression. So now shear stress. Shear stress's sign convention is a little bit weirder. So I'm going to draw a circle, which is going to make it a little bit easier to visualize. You just want to check whether the arrows are pointing in the same direction or different directions. So torsion, both the downward pointing 10 and the rightward pointing 20 are both causing clockwise direction torsion. So at point A, they're both pointing to the right. And the shear, due to the 20 going across the side to the right, the 20 kilonewton shear V is also pointing to the right. So all three terms are pointing in the same direction. So in this case, I'm calling that the negative direction, so I am subtracting both terms. But if you wanted to add them together, you would get the same magnitude. Again, as long as they're both pointing in the same direction, both added or both subtracted, that's the important part. And I get negative 30.7 megapascals. Now point B, down on the bottom, both torsion terms going clockwise, they're both causing rotation to the left at point B, but shear is still pointing to the right. So the torsion terms and the shear terms are going opposite directions. So make sure your signs are opposite this time. So this is why I now have a plus term, positive term for torsion, because my torsion is now going the opposite direction at point B than it was at point A. This ends up giving me a value of 11.8 megapascals. And finally, point C, over on the far right, the clockwise rotation terms are both pointing downwards at point C, and the 10 kilonewtons shear stress is also pointing downwards, so all three of them pointing the same directions. I'm calling this the positive direction this time, so I'm adding all these numbers up, get a magnitude 25.9, because they all three, again, add to each other, 25.9 megapascals. And just when you thought you were done, you reread the problem statement and saw that there's one step left to draw these on a differential stress element. So let me start off by drawing my cross-sectional area for points A, B, and C. And I'm taking these same arrows like I did when I was doing shear stress, and I'm drawing those at points A, B, and C, where I show an arrow at A coming outwards in tension and a B pushing inwards in compression, at C pointing inwards in compression. And my shear stress, right at point A, down at point C, left at point B. Now, when I draw my differential stress element, what I'm going to do is I'm just going to take each of these purple and green arrows and just place them on the close side of my square, just so I keep sort of the orientation the same for all three of these. So for point A, my stress element is again pointing outwards and then pointing rightwards for shear stress. And if you want to turn this into the start of a Mohr circle problem, I can draw the top-down view of this stress element with my 224 in tension and my shear stress 30 as positive shear stress. Right? Repeat the same thing for point C, where I've got, again, compression forces, and that front surface kind of has a downward pointing arrow. So again, now I can draw this as a Mohr circle type problem, kind of looking at it from the right side this time, where I've got compression forces squeezing in, and that right-hand side arrow, is pointing upwards. One more time for point B, where again, I've got the inward compression arrows, and then I can rotate it again. I'm still going to draw it looking from the top down, just to sort of keep the orientations kind of similar to point A. And so that you can see that the shear stress from A and B are pointing in the opposite directions. And just based on my stress elements here, I'm seeing here right at the very end, on the Mohr circle little square drawing, when you have shear stress on your right-hand side pointing upwards, like the 30, that is positive. And when it's pointing downwards, like at point B, that is negative. So I actually might want to go back and actually change some of my signs from earlier on shear stress. But again, ultimately, I will still maintain positive and negative signs, super important for normal stress because that tells you tension or compression. Much less important, the sign convention for shear stress. Although it does become relevant later on when you're deciding which direction you want to rotate your object to align an axis.